Hello my dear students and viewers. In this lecture we are going to discuss two ways of measuring how fast a convergent sequence converges to its limit value. In any optimization algorithm or in any optimization iterative process, to reach an optimum solution or a stationary point of an optimization problem, we commonly proceed as follows. We start from a given initial point x0, then we move to next iterative point x1, then from x1 by following a particular process of the optimization algorithm we reach at the next iterative point x3, and then from x3 we proceed to x4 and so on. So this x0, x1, x2, x3, x4 and so on generates a sequence, say xk. We devise optimization algorithms in such a manner that this generated sequence by the optimization algorithm converges to a point that is at least a stationary point, if not an optimum point of the given optimization problem. A major concern for the generated sequence xk that converges to a stationary point is that how fast this sequence xk converges to a stationary point. In this lecture, we endeavor to measure or to quantify fastness of the convergence of a sequence xk to its limit value. Agendas of this lecture are neatly two topics. Those are quotient convergence order and root convergence order of a convergent sequence. Both these order of convergences are measures to find how rapidly a sequence converges to its limit. Before getting into the discussion of quotient order and root order, let us quickly relook what we have done in the previous lecture. In the previous lecture, we were discussing the ideas about supremum and infimum of a set of real numbers, then the notions of sequence and its convergence were discussed. Thereafter, without having a knowledge about the limit of a convergent sequence, to check the convergence, we discussed the idea of a quasi-sequence. Furthermore, the idea of subsequence of a sequence was also talked. Finally, we ended up the lecture with the ideas of limit superior and limit inferior of a sequence of real numbers. Today, we shall use this idea of limit superior to define the quotient order or the root order of a convergent sequence. This quotient order and root order of convergence of a convergent sequence are measures of fastness of the convergence of a convergent sequence in Rn that converges to, say, the vector x bar. Note that by measuring how fast this sequence of real numbers converges to 0, we can get a sense how fast this sequence xk of vectors converges to its limit x bar. Note that how fast is the convergence epsilon k to 0 can be identified by comparing the smallness of the consecutive terms epsilon k plus 1 and epsilon k of the sequence epsilon k. We take two general consecutive terms epsilon k plus 1 and epsilon k and see if there exists some real number p greater than or is equal to 1 such that epsilon k plus 1 is less than or equal to some positive constant gamma times epsilon k to the power p. If such a p exists for which this relationship is true for all k or for all index k after certain index number say k naught, then we say that epsilon k converges to 0 with order of convergence at least p. Notice that through this relationship we can identify how small is this number epsilon k plus 1 by knowing how small is the previous term epsilon k. Let us now define mathematically the quotient or Q convergence of a sequence of order at least p. During our discussion, in order to avoid unnecessary complications, we consider that no terms in epsilon k is 0. So we are considering that epsilon k is always greater than 0 for every k. We now define Q convergence of order at least p. We say that a sequence xk in Rn converges to x bar with Q convergence of order at least p greater than equals to 1 if there exists a positive constant gamma such that epsilon k plus 1 is less than or equal to gamma epsilon k to the power p for all indices k's greater than or equals to some index number k naught, where epsilon k is defined by the distance between xk and x bar. Now from this definition of Q convergence of order at least p, we immediately note that if a sequence xk converges to x bar with Q convergence of order at least p, then for any q that lies in between 1 and p, the sequence xk converges to x bar with Q convergence of order at least q. This fact is very simple to realize because if xk converges to x bar with Q convergence of order at least p, then we have epsilon k plus 1 less than or equal to gamma times epsilon k to the power p. Now as xk converges to x bar, so epsilon k converges to 0, and hence after certain index number we can assume that epsilon k is less than 1, and hence for any q less than or equal to p, we have epsilon k to the power p less than or equals to epsilon k to the power q, and hence ultimately epsilon k plus 1 is less than equal to gamma times epsilon k to the power q, and thus xk converges to x bar with Q convergence of order at least q, and therefore this definition of Q convergence of order at least p does not characterize uniquely the order p to measure the speed or fastness of the convergence xk to x bar. Here we note that this value of p certainly measures a speed of convergence of epsilon k to 0, because the bigger the value of p, the faster is the convergence of epsilon k plus 1 to 0. Now, in order to identify a unique order of Q convergence, we consider the collection of all p values for which Q convergence is of order at least p. Then we go for taking supremum of all the p values and define a Q convergence order for the convergence of xk to x bar as follows. We denote Q of the sequence xk as the supremum of all the p values for which xk converges to x bar with Q convergence order at least p, which can further be identified as the supremum of all p values for which this inequality is true for the sequence epsilon k, and from this inequality we see that we get the sequence epsilon k plus 1 divided by epsilon k to the power p bounded above by the real number gamma. For a bounded above sequence of real numbers, we all know there exists a least upper bound, and hence this sequence has a finite and definite upper limit or limit supremum. We collect set of all those p values greater than 1 for which this limit supremum is a finite and definite quantity, which we denote by less than positive infinity. As in defining the Q convergence order, we consider ratio of or quotient of these two quantities, epsilon k plus 1 and epsilon k to the power p. We prefix the letter q, which stands for quotient, to define the convergence order and name it as Q convergence order. Now if let's suppose P star is equal to the Q convergence order of the sequence xk, then certainly limit supremum of epsilon k plus 1 divided by epsilon k to the power p star exists. Suppose this limit supremum is equal to mu, or let us subscript by q. This value mu q is called asymptotic constant of the convergence xk to x bar or epsilon k to 0. The word asymptotic is due to the fact that as the number k increases, the sequence epsilon k plus 1 divided by epsilon k to the power p star approaches the limit mu k, or the horizontal asymptote y is equal to mu q. This mu q value is also referred as rate of convergence. In fact, in the literature of iterative sequences or iterative process, these two terminologies, order and rate, they are used interchangeably. However, in our course, let us fix our attention with mu q to be called as rate of convergence, and qxk to be referred as order of convergence. However, as and when required, we may also refer this mu q as the asymptotic constant of the Q convergence. Now from this definition of Q convergence and the asymptotic constant, we have a few immediate notes. The first note is that the bigger the value of P star, the faster the convergence of xk to x bar. Mathematically, faster convergence is identified by lesser number of iterations required to reach in an epsilon neighborhood of the limit x bar. To realize the fact in this note 1, let us consider that say epsilon k converging to 0 with q order p star, and we consider a sequence epsilon k dash that converges to 0 with order q order p star dash, and suppose that p star dash is bigger than P star. Then for epsilon k converging to 0 of q order P star, we have epsilon k plus 1 less than or equals to gamma times epsilon k P star, and subsequently at the end we will find less than or equals to gamma to the power 1 plus P star square till P star to the power k minus 1 times epsilon 1 to the power p star to the power k. Here obviously we are assuming that this inequality is holding to be true for all indices k greater than equals to 1. So without just loss of generality or to avoid complications, we are considering here that this k naught value to be is equal to 1. So finally we get epsilon k plus 1 less than or equals to gamma to the power p star whole to the power k minus 1 divided by p star minus 1 times epsilon 1 to the power p star whole to the power k, which is equal to some constant beta times some theta to the power p star to the power k, where this theta is equal to epsilon 1 into gamma to the power 1 by 1 minus p star. You please figure out why this theta is equal to this, and you also please find out what is a possible value of this constant beta. Now certainly this theta can be assumed to be less than 1 because the sequence epsilon k is converging to 0. So after certain index number k naught, say, we certainly have epsilon k naught times a positive constant that is less than 1. Now without loss of generality, we can start our sequence with the first element epsilon 1 to be epsilon k naught, and then we can realize that this theta is certainly less than 1. Similarly, for epsilon k dash converging to 0 with q order at least p dash, we will have epsilon k plus 1 dash less than or equals to some beta dash times theta dash to the power p star dash to the power k. Now here you note that this theta dash and theta both are positive constants less than 1. As p star is smaller than p star dash, to realize epsilon k plus 1 dash less than a precision, say epsilon, we require lesser value of this index k than the index k over here to realize epsilon k plus 1 less than this precision epsilon, and thus as the bigger the value of p star, the faster the convergence of the sequence xk to x bar. Now in the next note, I will try to show the effect of molar value of the asymptotic constant in finding faster convergence. We needly have a smaller value of mu q identifies faster convergence. By this I mean for a given p star, as the q order of convergence of two sequences epsilon k converging to 0 and epsilon k dash converging to 0, both are of order p star if we have mu q for this sequence and mu q dash for this sequence, with mu q a smaller value than mu q dash, then this convergence epsilon k to 0 is faster. That means it will reach in a small neighborhood of 0 with less value of k than that for epsilon k dash. To exactly feel the effect of the value of this asymptotic error constant mu q, let us consider a specific value of p star, say equals to 1, and we choose two values mu q and mu q dash as say zero point 0.1 and another 0.9 respectively. So we take mu q to be say 0.1 and mu q dash to be 0.9. These mu q's, are also referred as asymptotic error constants because they are given by the sequence epsilon k, which is crudely referred as the error that the distance from the kth element of the sequence to the exact limit or the limit of the sequence xk. Now for mu q is equal to 0.1, we see that we have limit supremum of epsilon k plus 1 divided by epsilon k to the power p star, which is equal to 1, is equal to 0.1, which implies epsilon k plus 1 divided by epsilon k is less than equal to some gamma value which is very close to the value 0.1. Instead of considering very close to 0.1, we just consider here exactly the value 0.01. This is just to sense how fastly epsilon k converges to 0. Now from this relationship, every one index k adds another digit of accuracy for the convergence epsilon k to 0. You can take an example and find out why is this happening. That if, let's suppose, we are taking epsilon k is equal to 0.98, then immediately in the next term epsilon k plus 1, we have epsilon k plus 1 less than equal to epsilon k into 0.1 or a value close to 0.1, which is equal to 0.098. So we get a digit of accuracy, 0 is coming here to the limit value, exact limit value 0. If you consider epsilon k plus 2, then we'll find that this is less than equal to 0.0098. So as we progress in each and every iteration, we are getting an increased digit of accuracy. Here 1, here 2, then here 3 and so on. So when we have mu q to be exactly 0.1 or approximately nearby 0.1, then we can expect that consecutive terms epsilon k's are adding one digit of accuracy for the convergence epsilon k to 0. Now for mu q dash is equal to 0.9, we can see that if epsilon k is equal to 0.98, then the inequality epsilon k plus 1 divided by epsilon k less than or equal to some value around mu q dash, or simply let us consider approximately 0.9 itself, then epsilon k plus 1 is less than equal to 0.9 into 0.98, which is equal to 0.882, which does not have any digit of accuracy to 0.000. Now if you compute epsilon k plus 2, then also you will find that it is 0.7938, which also do not have any accurate digit with 0.000. Not only that, till epsilon k plus 21, we will not have any digit accurate with 0.000. Only at epsilon k plus 22 we will have just a single digit accurate with the value 0.000. So when mu q dash is equal to 0.9, then a digit of accuracy is achieved when every index is increased by at least 22. So if we associate the sequence epsilon k as an iterative sequence in an iteration process, that means in the first iteration of the iteration process we get epsilon 1, then in the second iteration we get the second element of the sequence, in the third iteration we get the third element of the sequence and so on. Then in this iteration process we see that for mu q is equal to zero point 0.1, every iteration adds another digit of accuracy with the limit value 0.000. However, when mu q dash is equal to 0.9, then every 22 iterations adds another digit of accuracy. These observations reflect the effect of the value of the asymptotic error constant mu q in an iteration process. We realize here that as the value of mu q smaller, that faster is the iteration epsilon k to converge its limit 0. You know, this value of asymptotic error constant is also dependent on the choice of the norm being used while defining epsilon k is equal to norm of xk minus x bar. If we alter the expression of the norm, then the asymptotic rate or asymptotic error constant mu q gets changed. We write it out as a note 4, that asymptotic error constant is norm dependent. To get a sense why this asymptotic error constant is norm dependent, we consider an example that we take Lebesgue 2 norm or the Euclidean norm in the R2 plane. Here we are considering x is having two components, x1 and x2. So norm 2 expression is given by under root of x1 square plus x2 square, and also consider the infinity norm, which is given by maximum of the absolute value of the components, and take the sequence xk in R2, which is defined by 1 upon 2 to the power k, having first component 1, second component 0, when k is odd and when k is even, xk is the vector 1 by root 2 times 1 upon 2 to the power k multiplied with the vector having components 1 and 1. For this sequence, we see that norm 2 of xk is equal to 1 upon 2 to the power k, and we can show that this sequence xk converges to the null vector with q convergence rate is equal to 1. With this convergence rate is equal to 1, the limit supremum of epsilon k plus 1 divided by epsilon k is equal to limit supremum of norm xk plus 1 divided by norm xk, which gives us the value of mu q, the asymptotic error constant, as half. However, with norm infinity, we see that norm xk infinity is equal to 1 upon 2 to the power k when k is odd and 1 upon under root 2 into 2 to the power k when k is even, and hence norm of xk plus 1 divided by norm xk is equal to 1 upon 2 root 2 when k is odd and 1 upon root 2 when k is even, and hence limit supremum of this ratio is equal to 1 upon root 2, which is different than the earlier asymptotic error constant half, and hence we see that this asymptotic error constant is norm dependent. Now next I would like to mention one more point on the definition of Q convergence order. Here you might ask me a question that why have I considered P to be greater than or equals to 1? The reason behind this is that the value of P less than 1 does not make any sense. By that I mean, if P is less than 1, then limit supremum, or simply limit to avoid unnecessary complications, epsilon k plus 1 divided by epsilon k to the power p equals to some mu greater than 0 does not imply that the sequence epsilon k is converging to 0, but convergence of epsilon k to 0 is a prior assumption before defining the Q convergence order as the value P. So if P is less than 1, then the Q convergence order does not really make any sense. Now I keep it as a home task to prove that for p less than 1, limit of this ratio is equal to mu greater than 0 does not imply that epsilon k is a sequence converging to 0. To prove it, just you try to figure out that epsilon k is greater than some positive quantity, say beta, maybe after certain index k naught. Now I would like to mention two more points, that the value of p is a real number, not necessarily a positive integer. As a final note, let me mention the process of finding the Q convergence order as the value say P star. To show that the Q convergence order of a sequence say xk is equal to P star, as per the definition, we have to show that this P star is the supremum most value for which limit supremum of the ratio epsilon k plus 1 divided by epsilon k to the power p star is a finite and definite quantity, but for any value which is slightly bigger than p star, say epsilon bigger than 0, the limit supremum of the ratio epsilon k plus 1 divided by epsilon k to the power p star plus epsilon is not a finite quantity. We shall consider a few examples where we will try to find the Q convergence order. Before that, let me mention a few special nomenclature related to Q convergence order. You know, iterative processes with Q convergence order 1 or 2 play an essentially important role in the theory of optimization. So we introduce some terminologies that will be useful later during identification of order of convergence of numerical algorithms to solve optimization problems. For P star is equal to 1, let us suppose the asymptotic error constant be mu. If we find that this asymptotic error constant mu is lying in between 0 and 1, then we say that the sequence epsilon k converges to 0 or the sequence xk converges to x bar as quotient linear or q linear. If mu is equal to 0, then we say the convergence of xk to x bar is superfast or superlinear. In case the value of mu is equal to 1, then we say that the convergence is q sublinear. If the value of p star is equal to 2 and the asymptotic error constant mu given by limit supremum of epsilon k plus 1 divided by epsilon k square is positive, then we say the convergence of xk to x bar as q quadratic. Similarly, if p star is equal to 3 and the asymptotic error constant is positive, then we say the convergence as q cubic and so on. Some references do not include this restriction mu to be greater than 0. However, this is a common restriction and hence I have mentioned here that mu to be greater than 0. But notice that in defining Q linear, Q superlinear or Q sublinear, we need to have this mu value lying in the closed and bounded interval 0 to 1. Because if mu is bigger than 1, then in that case epsilon k may not converge to 0. Now you might ask me a question, that why have I named linear, superlinear, sublinear, quadratic and all. You know, this linear is due to the fact that when P star is equal to 1, then in that case, this epsilon k plus 1 is approximately equal to mu times epsilon k. This exhibits a linear relationship between epsilon k plus 1 and epsilon k. Similarly, when P star is equal to 2, epsilon k plus 1 is approximately equal to mu times epsilon k square, which exhibits a quadratic relation between epsilon k plus 1 and epsilon k. Thus the nomenclatures linear and quadratic. These superlinear and sublinear are due to superlinear is faster than linear, sublinear is slower than linear. I will come back to this point of linear, superlinear, sublinear and quadratic. After a while, let me consider a few examples, and after the examples, I will show geometrically that in a log scale, the relationship between the index number k and log epsilon k is linear when epsilon k converges to 0 with q linear convergence rate. Similar will be the facts for superlinear, sublinear and quadratic. Let me consider the first example to execute the convergence rate as the sequence epsilon k is equal to some fraction to the power k where a is a constant lying in between 0 and 1. Here we can see that epsilon k plus 1 divided by epsilon k is equal to a, which converges to a, and for any number slightly bigger than 1, let's say 1 plus epsilon, we see that with p is equal to 1 plus epsilon k plus 1 divided by epsilon k to the power 1 plus epsilon, where epsilon is any number greater than 0. This ratio diverges to positive infinity. These two facts proves that epsilon k converges to 0 with q convergence rate is equal to 1, or this convergence is q linear, because the mu value is in between 0 and 1 and p star is equal to 1. Let us consider the next example as the sequence epsilon k is equal to 1 upon k. For this sequence, we see that epsilon k plus 1 divided by epsilon k converges to 1, and for any number slightly bigger than 1, we get epsilon k plus 1 divided by epsilon k to the power 1 plus epsilon diverges to positive infinity. And hence we have p star is equal to 1 with asymptotic error constant is equal to 1. So this convergence is q sublinear. I would like to consider the next example as the sequence epsilon k as 1 upon k to the power k. For this sequence, please check that epsilon k plus 1 divided by epsilon is k converging to 0, and for any epsilon greater than 0, epsilon k plus 1 divided by epsilon k to the power 1 plus epsilon is diverging to positive infinity. And therefore convergence of this sequence epsilon k to 0 is q superlinear. Let me consider sequence given by a recursion relation. Let's suppose epsilon 1 is equal to 1 and epsilon k plus 1 is defined by half times natural logarithm of positive square root of epsilon k plus 1 for every k 1, 2, 3 and so on. For this sequence, epsilon k plus 1 divided by epsilon k is equal to, you note that 1/4 of natural logarithm 1 plus epsilon k divided by epsilon k, and note that this ratio is less than 1 for any positive epsilon k, and hence epsilon k plus 1 divided by epsilon k is less than 1 and as well greater than 0. This sequence epsilon k is then monotonically decreasing and bounded below by 0. Therefore, the sequence epsilon k is convergent, and as this ratio is less than 1 by 4, we have limit epsilon k is equal to 0. And notice that limit of this ratio epsilon k plus 1 divided by epsilon k is equal to 1 by 4, since this encircled portion converges to 1 as epsilon k tends to 0. Also see that for any given epsilon greater than 0, limit of epsilon k plus 1 divided by epsilon k to the power 1 plus epsilon is equal to positive infinity. So this one. These two limits shows that epsilon k converges to 0 with q linear convergence and asymptotic error constant as 1/4. Now let me give you two homework to identify q convergence order. Find q convergence order of the sequences, say epsilon k is equal to some fraction a in between 0 and 1 to the power say 2 to the power k. You can find that this convergence of epsilon k to 0 is q quadratic. Also find the q convergence order of the sequence epsilon k given by 1 plus 2 upon 2 to the power k plus 1 divided by k plus 2 to the power k. You will find that this convergence epsilon k to 0 is q linear with asymptotic error constant is equal to 0.5. Now here I have gone through several examples where we have found superlinear, sublinear, linear as well as a quadratic q convergence. Let me consider particular cases of all these q convergences, and in a log scale let us try to find out the relationship between the index number k and log epsilon k. Then we can geometrically sense why the terminologies q linear, q sublinear, q superlinear, q quadratic, etc. We consider to write different cases with different colors. Let's say the first example, epsilon k is equal to 1 upon 2 to the power k. For this sequence, you can find that it is q linear. Consider epsilon k to be 1 upon k. This is q sublinear. Consider epsilon k is equal to 1 by k to the power k, which has q superlinear convergence. And the last example, as epsilon k is equal to 1 by 2 to the power 2 to the power k. This has q quadratic convergence. For the first example, we see that k and natural logarithm of epsilon k is related by log epsilon k is equal to minus k times log 2. So the relationship between k and log epsilon k is given by the trend of y is equal to minus ln 2 into x. If I draw this curve y is equal to minus ln 2x, that gives us a line passing through origin, and the sequence epsilon k takes a value in the plane of k and ln epsilon k. This point at k is equal to 1, at k is equal to 2, this point at k is equal to 3, this point, and so on. So this sequence epsilon k exhibits a linear relationship between k and ln epsilon k. For this sequence, we see that the relationship between k and ln epsilon k is given by ln epsilon k is equal to minus ln k, which follows the curve y is equal to minus ln x, which is a curve of this type. At k is equal to 1, the sequence ln epsilon k takes a value 0. At k equals to 2, the sequence takes this value. At k is equal to 3, the sequence takes up this value, and so on. Note that this green curve lies above the line y is equal to minus ln 2x. For the third sequence epsilon k is equal to 1 upon k to the power k, we get ln epsilon k is equal to minus k ln k, which follows the curve y is equal to minus x ln x. This curve has graph somewhat like this, and the fourth sequence epsilon k is equal to 1 upon 2 to the power 2 to the power k. We get ln epsilon k is equal to minus 2 to the power k ln 2, which follows the curve y is equal to minus ln 2 into 2 to the power x. This curve has graph somewhat like this, which is like inverted parabola. And so from all these four curves, we see that the trend of the green curve is that as k gets larger and larger value, this green curve is always above this orange line. This violet curve, which has superlinear convergence, lies below the orange line, maybe after certain index number, and this sky blue curve, which has q quadratic rate of convergence, follows the trend of a parabola. From these four graphs, we can then interrelate why all these four sequences are converging to 0 respectively with q linearity, q sublinearity, q superlinearity, and q quadratically respectively. Now we see that for a given epsilon greater than 0, for the first sequence we have epsilon k less than epsilon when the index number k is bigger than some positive constant times log 1 upon epsilon. For the second sequence, epsilon k is less than epsilon when the index number k is bigger than 1 upon epsilon. And for the fourth sequence, we have epsilon k less than epsilon when the index number k is bigger than some positive constant times log 1 upon epsilon. When for a given epsilon greater than 0, we need at least log of 1 upon epsilon number of iterations to reach epsilon k less than epsilon, then we can estimate that the order of convergence of the sequence is equal to 2. When we need at least log 1 upon epsilon or a constant multiple of it number of iterations to realize epsilon k less than epsilon, then we can estimate that the order of convergence is equal to 1. In fact, there is a precise result to estimate the order of convergence of a sequence epsilon k, which let epsilon
States
k be a
that
sequence that converges to 0 and p is greater than 1, then the q order of convergence of the sequence epsilon k is equal to p if and only if p is equal to limit infimum of the ratio ln epsilon k plus 1 divided by ln epsilon k. We will not prove this result in detail. A proof of this result can be found from a paper of the journal JOTA entitled On Q Order and R Order Convergence by a famous optimizer, Professor F. A. Potra, which came out through the Journal of Optimization Theory and Applications in the 63rd volume in the year of 1989. In this paper, you please look at the proof of the proposition 1.1 on page number 416. But I will give you a sense why this result is happening to be true. You notice that if the Q order of convergence of epsilon k is equal to P, then we have limit supremum of epsilon k plus 1 divided by epsilon k to the power P, a finite and definite quantity, let's suppose mu, then we see that epsilon k plus 1 or a subsequence of the sequence epsilon k will follow the trend of epsilon k plus 1 is equal to mu times epsilon k to the power p. Now we consider to apply log on this approximate equation. On both the sides you will get log epsilon k plus 1 approximately equal to log mu plus p times log epsilon k. Now divide on both the sides by log epsilon k and then take k tends to infinity. You will get that p approximately equals to log epsilon k plus 1 divided by log epsilon k. And the same expression is appearing over here to estimate the exact order of convergence of the sequence epsilon k. So to estimate the order of convergence of a sequence, you may compute log epsilon k plus 1 divided by log epsilon k and then take its limit infimum. You will get the value of the order of convergence. Now I will next move for defining root convergence order of a sequence. This notion of root convergence order is possibly motivated by two facts. The first is that the asymptotic error constant mu for Q convergence is norm dependent, and also for some sequences Q convergence order may not exist. In order to eradicate these two drawbacks of Q convergence, the notion of root convergence has been introduced. Before getting into the definition of root convergence order, let me give you an example in which we will see that for some sequences Q convergence order may not exist. Consider the sequence epsilon k defined by 2 to the power minus 2 to the power k when k is even and 2 to the power minus 3 to the power k when k is odd. For this sequence, please try to show that epsilon k plus 1 divided by epsilon k for this sequence limit supremum is equal to positive infinity, and hence for any given epsilon greater than 0 we have limit supremum of the sequence epsilon k plus 1 divided by epsilon k to the power 1 plus epsilon is also positive infinity. So we don't have any p greater than or equals to 1 for which limit supremum of this ratio with p over here is a finite and definite quantity. So for this sequence epsilon k, although it is converging to 0, it does not have any q convergence order. much pretty fact is the following, that you notice that this epsilon k is such a sequence which is smaller than the sequence epsilon k dash is equal to 2 to the power minus k, which converges to 0 with q order of convergence is equal to 1. So it is expected that this sequence epsilon k must reach to 0 faster than the sequence epsilon k dash. But unfortunately, this sequence do not have any q convergence order, but this sequence epsilon k dash has q order of convergence is equal to 1. Now let me define the idea of root convergence order or R convergence order. Here this capital R stands for the word root. Notice that q order of convergence was motivated by the inequality epsilon k plus 1 less than or equals to some positive constant gamma times epsilon k to the power p. If you see that for the sequence epsilon k, consecutive terms epsilon k plus 1 and epsilon k is related by this inequality, maybe after certain index number, say k naught, then we say the sequence epsilon k has at least p q order of convergence. If p is equal to 1, then we see that this inequality gives us epsilon k less than or equals to gamma times epsilon k minus 1, which is further less than or equal to gamma square epsilon k minus 2, and so on. Ultimately we will reach at gamma to the power k minus 1 epsilon 1, provided we are considering here this k naught without loss of generality to be equals to 1. So from here we see that epsilon k plus 1 is less than or equals to gamma to the power k times epsilon 1. If the value of gamma lies in between 0 and 1, then the sequence epsilon k decreases rapidly as a geometric progression or geometric sequence gamma to the power k with the ratio is equal to gamma. If however the value of p is greater than 1, then this inequality will reduce to epsilon k plus 1 is less than equal to some positive constant beta times some number alpha to the power p to the power k. Again here, if alpha is lying in between 0 and 1, then we see that this sequence epsilon k converges to 0 as rapidly as the sequence alpha to the power p to the power k. Now by considering geometric average of the sequence epsilon k, we see from this inequality that epsilon k to the power 1 upon p to the power k is bounded by some number, say beta bar. So in compared to considering limit supremum of the ratio epsilon k plus 1 divided by epsilon k to the power p, we consider limit supremum of epsilon k to the power 1 upon p to the power k and check if this limit supremum is a finite and definite quantity. Then you consider supremum of all p values greater than 1, for which limit supremum of epsilon k to the power 1 upon p to the power k is a finite and definite quantity, and define it to be R convergence order of the sequence epsilon k. Or in a more erudite fashion, consider here supremum over p greater than equals to 1, and then go for taking limit supremum of this expression when p is greater than 1, and go for taking limit supremum of epsilon k to the power 1 upon k when p is equal to 1. Check both these limits and check their finite and definiteness. Collect all the p's, p is equal to 1 or p greater than 1, for which these two limits are existing, and take supremum most value of all those p values as the root convergence order of the sequence epsilon k. This limit supremum value is called the asymptotic error constant for root convergence, and we denote it by mu r, which is equal to limit supremum of epsilon k to the power 1 upon pk for p greater than 1, and for p is equal to 1 it is limit epsilon k to the power 1 upon k. Now interrelating the concepts of root convergence order and Q convergence order, I will consider to discuss two particular results. Those are as follows: that if norm of xk minus x bar is less than or equals to some positive constant where eta k is a sequence converging to 0 with Q convergence order at least p greater than 1, then the R convergence order of the sequence epsilon k is at least p. The proof of this result is very simple. A straightforward calculation will reveal why this result is true. We notice that from the given condition, epsilon k is less than or equals to eta k, where eta k has Q convergence order at least p, we get epsilon k plus 1 less than equal to eta k plus 1 less than equal to some positive constant gamma times eta k to the power p, which is further less than or equals to gamma to the power 1 plus p into eta k minus 1 to the power p square. Keep moving with reducing eta k minus 2, eta k minus 3 and so on. You will ultimately end up with less than or equals to gamma to the power p to the power k minus 1 divided by p minus 1 times eta 1 to the power pk, provided we are assuming that this inequality is true for every k greater than equals to 1. Now this entire expression can be written in the form of some beta times theta to the power p to the power k for some beta greater than 0 and theta lying in between 0 and 1, which can be found due to the fact that this eta k tends to 0. So ultimately we are getting this epsilon k to the power 1 upon p to the power k is bounded above, and hence the R order of convergence of the sequence epsilon k is at least the number p. So from this result we can then conclude that if the Q order exists, then the Q order must always be less than or equals to the R order of convergence of the sequence epsilon k. Now next I will end up with mentioning a result that states that let epsilon k be a sequence converging to 0, then if there exists p greater than or equals to 1 such that the limit epsilon k plus 1 divided by epsilon k to the power p exists and greater than 0, then both R order and Q order of convergence of the sequence epsilon k are equals to the value p. This result is very easy to perceive. I am keeping this as a home task, and as this home task will require some time to prove, I am keeping this as the only question for the entire lecture. Before ending up this lecture, I also would like to mention one of the finest references for order of convergences of a sequence converging to zero, which is a book by Ortega and Ringbold entitled Iterative Solutions of Nonlinear Equations in Several Variables, which came out through Siam in the year of 2000. You please look at the chapter 9 of this book, where you will find a rigorous mathematical discussion about this quotient convergence order or root convergence order and their rigorous interrelationships. Note that in the root convergence order, we take the kth root or the p to the power kth root to define the R convergence order. Thus, the term root is prefixed with this type of convergence order. Interestingly, notice that this root convergence order is motivated by these inequalities, which is concerned about overall rate of decrease of the sequence epsilon k. However, in quotient convergence order, we were concerned about decrement of the sequential terms over each individual step epsilon k to epsilon k plus 1. With this comment, I end up this lecture and extend a sincere thanks for your kind attention. Thank you. Thank you all.